Welcome to Recursion Review 3 out of 3, Recursive Backtracking Review. As a refresher, recursive backtracking is used to find solutions by trying partial solutions or paths and then abandoning them if they're not suitable. So recursive backtracking is very similar to exhaustive search, where we have to keep track of the choices we made so far. Um, However, it's a little different in terms of we're exploring a single path and backtracking if it doesn't work out, instead of necessarily trying to generate all possible combinations or permutations. One pattern you'll see for almost every single recursive backtracking problem is choose, explore, and unchoose. So choosing is making a choice and updating the current path. So this is like adding a possible value or option to the path or list of items you're building up. Exploring is making a recursive call with that update, and the unchoosing is undoing the choice that we made in the choose step. So removing that option or value we added to our path or list of values that we made in choose. Choose, explore, unchoose. Add the value, make a recursive call, remove that value we added. Decision trees are also helpful with backtracking, and they serve the same purpose as exhaustive search. So go check out that review video if you want a refresher on decision trees. But these can help build intuitions for recursive backtracking problems, as well as exhaustive search problems. So still very useful. Tips for recursive backtracking. Again, we will want to use public-private method pairs as they're conventional and considered good style. One difference between exhaustive search and backtracking problems are usually we'll build up a collection with recursive backtracking instead of a string like we saw in exhaustive search. Using decision trees are still helpful, and then always keep in mind the choose, explore, and choose pattern, as almost every single problem will use this to some degree. Let's practice. So the backtracking problem I chose for this review video is print subsets. So we're tasked with writing a recursive method, print subsets, that takes a list of integer values and prints out all subsets of that list. So if we were given the list 1, 2, and 3 and called print subsets on it, print subsets should print out the 8 subsets. Empty list, subsets including 1 element, subsets including 2 elements, and our subset of including 3 elements. And this method can print the subsets in any order, but it should preserve the relative order of values. So if we gave print subsets a list containing only 42 and 23, then we should print all 42s before 23s. And we can assume that the list has no duplicate values. And one massive hint we're given for this problem is that each subset can either be included or excluded. Each subset can either include or exclude each value in the list. So this tells us how to choose at each stage of our decision tree. Let's write pseudocode for this. So the so far is the subsets we are building up. And there's not really a clear count. However, there is a stop condition, and that's when we've considered all of the integers in the list. For our base case, when we want to stop recursing is when we've considered all the integers via the stop condition. And when this is the case, we should print our subset. Otherwise, we need to keep exploring and considering integers. When there are still more integers to consider, we want to choose a new integer, explore the chosen path, unchoose that integer, and then we also have the option of exploring what happens when we didn't choose that integer. So we're exploring all possibilities of when we added that integer to the subset we built up, and all subsets we could create via the second recursive explore call when we didn't add that integer to the subset we built up. We have two possible options for exploring, one where we added that integer to our subset, and one where we didn't. And this is how we're creating all the possible subsets. For each integer in the original list, we're generating all subsets with that integer, and we're also generating all subsets without the integer via two recursive calls. Let's code this up. So I hopped on over to Ed, and I created a private helper method, as well as pseudocode in our base case, where we considered all the integers, and recursive case, when there are still integers to consider, as well as added a call to that private method in our public print subsets method. First, let's decide on what parameters our private method will take. Well, we need some way of knowing when we've considered all of the elements in the list. To do this, we can use an int index to keep track of which index or which integer index we're currently looking at and are currently exploring. So this will tell us whether or not we've explored all the integers, as when an index is greater than or equal to the size of the list, we know for sure we've considered all of the integers and we've hit our base case. We also need our so far, the thing we're building up. We can use a list. We can use a stack. It's really up to you. A queue may even work, but usually for the choose, explore, unchoose pattern, we'll always be adding to the ends of a data structure and removing from the ends. A lot of times I've written this with a list, but for this example, we can also use a stack, right? We can just push the stack when we're choosing and popping from the stack when we're unchoosing, the exact same behavior. Really though, it's just personal preference. Whatever you like to use and whatever feels more intuitive, use that instead. And I'll call our stack so far. Great. Let's fill out the private method call in our public print subsets method. So this would be our list. The initial index we're looking at is 0, and our stack is empty. So we can create a new stack of integer and give that to our private helper method. Like we said, our base case, when we considered all integers, is when the index is greater than or equal to the size of the list. And when this is the case, we can just print our so far. Finally, for a recursive case, when there's still integers to consider, well, we have two options, right? We have the option of exploring all possibilities when we add that integer at that specific index to our subset, and all possible other subsets we can create when we don't add that integer. So for when we do add the integer, we can use our choose, explore, unchoose pattern. So we'll push the elements at index. To clean things up a little bit, let me save this to variable. So int element is equal to list.get index. Perfect. So we can push that element. We can explore with print subsets of list index plus 1. So this is our update where we're increasing our index to consider all future elements past this index we're initially on. And then we give it the same stack, but now with the element added to it. After we explore, we want to unchoose. So calling so far.pop or remove the element we added to the end of the list. And finally, we want to choose or explore all possible subsets where we didn't add the element of this index to our so far. So just print subsets of list index plus 1 and so far without the element at this index. Let's run this. Great. So this almost matches our expected outputs. Or does it match? It does. Awesome. Sorry, the order of the subsets doesn't matter. So even though the example output printed out the empty list first and then increased the size of the subsets, this solution started with the largest subsets at the top and then the smallest subsets at the bottom. Either way works since the order of the subsets doesn't matter, and we've maintained the relative order of elements within our so far collection. That's it for recursive backtracking, but this is so cool because we can distill almost any recursive backtracking problem down to the same pattern with maybe some slight variations, where we find our base and recursive cases, looking at the decision tree can help with this, and then using our choose, explore, unchoose pattern to explore all possible paths or solutions, and then removing from the collection that we're building up using pop or removing from the ends. And almost any backtracking problem can be solved like this. So hopefully this video will help you preparation for your quiz, and good luck. Yeah.